It is our largest collider in the world.
Magnetic monopoles are the manifestation of a magnetic charge.
While experimenting, scientists can get to a point where things get out of hand and put them in deep trouble. Movies portray scientific experiments gone wrong as the creation of a monster or something terrifying. But what's really terrifying is the reality of our magnetic field being under pressure from an experiment. Join us as we delve into the Earth's magnetic field that was cracked open by the activation of the Large Hadron Collider. And the outcome was totally unexpected. Large Hadron Collider, the history and purpose. Large Hadron Collider, also known as LHC, is the world's most powerful particle accelerator, which was constructed by the European Organization for Nuclear Research, popularly known as Cern. The plan to construct the LHC started in 1984, and it finally began in 1995. The construction required thousands of scientists and engineers from dozens of countries to design, plan, and build the LHC. And of course, it cost a lot of money, with the cost of materials and manpower minus the cost of running experiments amounting to nearly $5 billion. The LHC ran its first test operation on September 10, 2008, and it went well. But on September 18, an electrical problem in a cooling system resulted in a temperature increase of about 100 degrees Celsius in the magnets, which are meant to operate at temperatures near absolute zero. It took a while for the LHC to get fixed, and it restarted on November 20, 2009. Less than 2 weeks later, the LHC became the most powerful particle accelerator when it boosted protons to energies of 1.18 tera-electron volts. The LHC developed another problem on March 2010. A problem with the design of superconducting wire in the LHC required that the collider run only at half energy, and for that, the LHC was shut down in February 2013. It was restarted again in April 2015 to run at its full energy of 13 tera-electron volts. The next time the LHC would be shut down was in December 2018 for an upgrade which ended in July 2022. The purpose of the LHC project is to understand the fundamental structure of matter by recreating the extreme conditions that occurred in the first few moments of the universe according to the Big Bang model. For decades, physicists have used the so-called Standard Model for fundamental particles, which has worked well, but has weaknesses that include the inability to explain why some particles have mass. Discovery of Higgs boson. A decade has passed since humanity officially discovered what makes our existence possible. On July 4, 2012, scientists announced the observation of the Higgs boson, the elusive particle that lays the foundation for the matter that forms us and everything we see around us in the universe. This was courtesy of the LHC, which has aided the discovery of many important things as well as the Higgs boson. But what exactly is Higgs boson? The Higgs boson is simply a particle that gives other particles mass. But before its discovery, there has been a debate on whether the Higgs field exists. This discovery proved the existence of the Higgs field and its function as a mass-giving mechanism. In 2012, Francois Engler and Peter Higgs independently came up with the Higgs mechanism, and together they shared the Nobel Prize in Physics. On July 5, 2022, the LHC detector switched on all subsystems and started recording high-energy collisions at the unprecedented energy of 13.6 teravolts. The LHC has been put through years of upgrade and maintenance around the clock by operators, all for it to function at this high energy. After 3 years of this rigorous work, the LHC was set to run for close to 4 years at the record energy of 13.6 trillion electron volts, providing more precision as well as higher discovery potential. However, to the surprise of the physicist, when the LHC was turned on, they saw something peculiar, which they believed could be caused by magnetic monopoles. This further brings us to another question. Do magnetic monopoles actually exist? Magnetic monopoles. A magnetic monopole is a particle that is an isolated magnet with only one magnetic pole, which could be a south pole without a north pole or a north pole with a south pole. Or you can simply say, a magnetic monopole is a manifestation of an electric charge. The only known elementary particles that have an electric charge are electric monopoles. But in the case of magnetic monopoles, scientists have been trying to prove their existence a long time ago. Till the time this video was made, magnetic monopoles have not been found to exist by empirical evidence, but just by theoretical consideration. The theories that have predicted the existence of magnetic monopoles include the superstring theories and the grand unified theory. The concept of quantized fields and the compactness of the U1 gauge group have led to the idea of unification. In 1974, physicists began exploring the idea of unification, which led to the development of the grand unified theories. And these theories in turn predicted the potential stability and decay of protons, the existence of new super-heavy particles, and also the existence of magnetic monopoles, as demonstrated by Gerard Hooft and Alexander Polyakov. How the idea of monopoles started. It's almost as if scientists are just crazy about the idea of something in their imagination, but that's not true. It all started in the 19th century when little was known about magnetism and electricity. The widely accepted theory is that electric charge exists and that it has two types. It is also known that like charges repel while unlike charges attract, and that these charges in motion created currents known as electricity today. That's not all. It was also known that permanent magnets had one side that acted as a north pole and the other as a south pole. However, scientists could not find a way to split a permanent magnet. In other words, no matter how much you chopped up a permanent magnet, you'd never end up with a north pole or a south pole by themselves. This also means magnetic charges only came paired up in a dipole configuration. The electromagnetic universe could make more sense to us thanks to several discoveries made during the 1800s. We learned about induction, which is the process by which moving electric charges generate magnetic fields, and how changing magnetic fields in turn induce electric currents. There was also the discovery of electromagnetic radiation, and how accelerating electric charges can emit light of varying wavelengths. The combination of this knowledge made it known that the universe was not symmetric in terms of electric and magnetic fields. Maxwell's equations only have electric charges and currents. There are no fundamental magnetic charges or currents, and all magnetic properties that we observe are actually caused by electric charges and currents. From a physics theoretical point of view, it's very simple to modify Maxwell's equations to include magnetic charges and currents, and the ability for objects to also possess a fundamental magnetic charge, either an individual north or south pole. When you add these terms, Maxwell's equations change and become completely symmetric induction, which now works the other way around. Moving magnetic charges are known to generate electric fields, and a changing electric field can induce a magnetic current, thereby causing magnetic charges to move and accelerate within a magnetic current while carrying material for a long time. All of these were just speculations until scientists discovered the roles that symmetries play in physics and the quantum nature of the universe. There's every chance that electromagnetism is symmetric between electric and magnetic components at some higher energy level, and that we live in a low-energy, broken symmetry version of that world. One of the scientists that were quick to recognize the existence of magnetic charges was Pierre Curie. He demonstrated something remarkable. If there was even one magnetic charge anywhere in the universe, it mechanically implied that electric charges should be quantized everywhere. This is fascinating because when it comes to quarks, an elementary particle that combines to form hadrons, not only are electric charges quantized, but they are quantized in fractional amounts. None of these proves that magnetic monopoles exist, rather it merely suggests that they might, but scientists never gave up on looking for monopoles. How scientists have been looking for magnetic monopoles? No, the scientists can't stop now. They have been on it for a long time. In 1981, experimental physicist Blas Cabrera built a cryogenic experiment involving a coil of wire explicitly designed to search for magnetic monopods. He thought that by constructing a coil with 8 loops, if a magnetic monopole ever passed through the coil, he would see a specific signal. Due to the electric induction that would occur, passing one end of a permanent magnet into or out of a coil of wire induces a current, but passing a magnetic monopole through that coil of wire should induce an electric current that corresponds to exactly 8 times the theoretical value of the magnetic monopole's charges due to the 8th loops. According to Cabrera's experimental setup, if a dipole passed through, there would be a signal of +8, which would be followed by a signal of -8, allowing the two scenarios to be distinguished. Cabrera left his setup at his office and went home. He returned the next day and was surprised by what he saw. The experiment produced a single signal that was nearly identical to what a magnetic monopole should produce. This sparked a lot of interest in the project. It also gave rise to a series of questions, one of which is, do we actually live in a universe with magnetic monopoles? But while these questions were not answered, there was an influx of copycat experiments. Many of these experiments had more loops in their coils, but no one else ever saw anything resembling a magnetic monopole. However, Cern and its scientists took it upon themselves to search for monopoles. LHC to the rescue. Of course, Cern has the world's largest and most powerful particle accelerator, which consists of a 17-mile or 27-kilometer ring of superconducting magnets in a series of accelerators. It fires high-energy particles through the apparatus like a bullet is fired through a gun. 328 feet below the ground exists a collider that blasts a beam of protons in one direction, while another beam travels in the opposite direction at maximum speed. The particles collide at 99.99 the speed of light. And every time protons collide, a complex spray of other particles is produced. Many of these particles have a lifetime of less than a second, but they leave a trail of subatomic breadcrumbs. These are what the scientists follow by depending on two highly complex detectors that follow their trail. These detectors have helped them to see the fundamental building blocks of our universe. One of these detectors is Atlas, which is about 148 feet or 45 meters long and 82 feet tall. Atlas assisted in the discovery of the Higgs boson and has also been used with other particle detectors like CMS to investigate topics that are only discussed in science fiction, such as whether other dimensions exist, what type of unifying force exists in the universe, and whether there is evidence of dark matter. Atlas and CMS were the only detectors dedicated to solving the Higgs boson mystery. It is one thing to smash particles together at nearly the speed of light, and another thing to interpret the data generated by those collisions. Particles collide about 600 million times per second in the LHC, and the information emitted by those crashes can tell us a lot about the inner workings of the atom and the forces that hold it together. But the problem is we can't record everything from the detectors. For example, Atlas could fill 100,000 CDs with data every second, while other detectors can only record a smidgen of data equivalent to about 27 CDs per minute. One of the biggest problems encountered by scientists occurred when they tested their theories about how particles behave. They contrast computer-simulated collisions with real-world collisions, and a difference between the two could show something previously unknown. The good news is a new class of experiments at the Large Hadron Collider at Cern have created conditions more likely to produce monopoles. Even though no monopoles have yet been discovered, the new experiment allowed researchers to get the likely properties of monopoles. The experiment gave course to future experiments and at the same time gave closure to previous experiments. Scientists can rule out the existence of certain types of monopoles and also have a better idea of whether the search for monopoles could proceed in the future. In the experiment, the LHC smashed together a different kind of particle, heavy ions in the form of lead nuclei. But because these particles contain hundreds of protons and neutrons, they can only collide at lower energies than single proton collisions. However, if these lead nuclei pass very close to each other, the interaction can produce something spectacular. The theory is based on a mechanism for producing electrons and their antimatter equivalent positrons. According to the Schwinger mechanism, which was proposed in the 1930s, a strong electrical field will interact with quantum fluctuations in a vacuum producing electrons and positrons, and a strong magnetic field should also produce north and south monopolies. Now, it's time for today's subscriber pick. Look at the image carefully. It looks like the perfect description of a CME accompanying a solar flare. In case you are still unable to picture what it could look like, you can picture something close to this. Rather than picturing a thing of beauty, the effect of the crack can be really terrifying. Stick around to find out reasons why the crack can be more dangerous than what it looks like. Limitations on magnetic monopoles. The Large Hadron Collider is an important tool for studying the potential existence of magnetic monopoles, as it is said to be able to produce magnetic monopoles at extremely high energy scales. Additionally, the upper limit to the temperature achieved during the hot Big Bang phase is determined by constraints imposed by observations of gravitational waves, which must be generated by inflation. If grand unification is relevant to our universe, it can only occur at energy scales exceeding the normal limit. This means if magnetic monopoles exist, they must possess a significantly high rest mass on the order of 10-15 TeV or higher. Now, after years of research and experiment, and the clue that hinted at the potential existence of magnetic monopoles, researchers found that the monopoles can't be less than 70 times the mass of a proton. This became the first strong limit on the massive monopoles. the crack. The best result of the experiment would have been the discovery of magnetic monopoles, but instead, the scientists were faced with what was unexpected. They discovered a crack in the Earth's magnetic field, and on top of that, it remained open for nearly 14 hours. This is a rare phenomenon known as a co-rotating interaction region known as CIR. The CIR is a large-scale plasma structure formed when fast and slow-moving streams of solar wind interact in the heliosphere's low and middle-latitude regions, which include the solar magnetic field and the solar winds. CIRs, like coronal mass ejections, CMEs, containing shock waves, have flung out from the Sun towards Earth and compressed the magnetic field. It usually results in stormy space weather, which usually manifests as beautiful roaring. CMEs, like solar flares, are caused by the twisting and realignment of the Sun's magnetic field, a process known as magnetic reconnection. When magnetic field lines tangle, they produce strong, localized magnetic fields that can break through the Sun's surface at active regions, resulting in CMEs. Typically, CMEs occur near sunspot groups and are frequently accompanied by a solar flare, though the two do not always occur simultaneously. During the Sun's 11-year cycle of activity, when the Sun is most active, CMEs swell in size as they travel away from the Sun after they're released. Larger CMEs can fill nearly a quarter of the space between Earth and the Sun. By the time they reach our planet, if a CME is large enough and travels faster than the solar wind, it generates a shock wave in which accelerated charged particles travel ahead of the CME, disrupting space weather conditions and intensifying geomagnetic storms. While CMEs produce beautiful auroras, they can also be destructive. Large CMEs can cause technological malfunctions, which would be a big trouble in today's world. For example, the Carrington event in 1859 disrupted the global telegraph system. There are even reports of operators getting electric shocks and sparks which ignited papers from telegraph machines. According to NASA, a CME accompanied a solar flare that hit Earth in 1989, causing an electrical blackout that lasted 12 hours in the entire province of Quebec, Canada. That incident cost Quebec's utility company, Hydro-Quebec, at least $10 million in damage. How CMEs cause so much havoc. CMEs can cause electrical current surges that overload power grids, resulting in widespread blackouts, and that is in addition to jostling the Earth's magnetic field. It can impair radio transmissions and increase radio static in the ionosphere. Usually, GPS systems are vulnerable to ionosphere disturbances, and GPS coordinates have been known to stray by tens of feet during a CME event. GPS uses radio signals to relay information between a satellite and a ground receiver, which causes the disruption. The radio signal passes through the ionosphere layer, which contains charged plasma that bends the path of the GPS signal in the same way that lenses bend light. Normally, GPS systems can compensate for this bending of the radio signal, preserving GPS accuracy during a CME event. However, the ionosphere can be so severely disrupted that GPS models are unable to keep track of such changes. Receivers are unable to calculate an accurate position, and also, Earth-orbiting satellites are vulnerable to CMEs, particularly those in high geosynchronous orbits, which is where the majority of communication satellites are located. Satellites can be struck by a high current discharged into the satellite or damaged when high-energy particles penetrate the satellite. When a CME causes a geomagnetic storm as a result, vulnerable satellites can be put into safe mode to prevent electronic damage. SpaceX saw firsthand the devastation the space weather can cause recently when a geomagnetic storm destroyed up to 40 Starlink satellites worth more than $50 million. The magnetic field protects us against solar storms caused by the Sun. It was previously thought that they opened and closed quickly, but we now understand that they stayed open for hours. Scientists have likened the phenomenon to a house whose window is left open during a storm. Although the house would deflect a larger part of the storm, the properties of the house won't remain in the same condition. Similarly, a magnetic shield absorbs the brunt of space storms, but some energy escapes, causing problems with satellites' radio communication and power systems. Now, the Sun is nearing its most active period in the solar cycle, around July 2025, and is already unusually active for this early in this cycle. This means that there's a big chance of seeing the aurora. Reasons why the crack is terrifying. There are good reasons why the crack should scare anybody. The first reason is that it is an effect of something going on in the Earth's magnetic field. But the most terrifying reason is losing the air we breathe. How can this happen? It would be a result of the solar wind once again. The sun's natural wind is so powerful that it can easily rip gases from a planet's atmosphere until there is no gas left in it. Scientists believe that this is most likely the reason why Mars has little life in it. Mars was most likely once similar to Earth without much water and a dense atmosphere, but unlike the Earth, its magnetic field disappeared billions of years ago. Mars's atmosphere was completely unprotected, and it was ripped away into space. When its atmospheric pressure fell low enough, its water began to evaporate and was carried away by the solar wind. Therefore, it is possible that without our magnetic field, our atmosphere, oceans, and life on Earth would perish in the same way. But before then, animal life would be affected on our planet. Humans aren't the only ones that use the Earth's magnetic field to guide them. A lot of birds, lobsters, salmon, bees, and even animals as small as fruit flies have biological compasses known as magnetoreceptors built into their bodies. During the winter, birds use this ability to migrate to warmer climates, and sea turtles use it to navigate the open ocean and find beaches to lay their eggs. This is why you see a lot of birds traveling in winter. These animals can do this thanks to their natural compasses. If we end up losing our magnetic field, many animals that rely on compass navigation could be in serious danger. For example, birds would stay in an unfavorable environment, which may lead to their deaths. Honeybees may become disoriented or searching for their hives, thereby affecting flower and plant pollination. Many other organisms may face extinction as their navigational abilities deteriorate, and in turn, every living organism will get affected. More concern and speculations. In the midst of uncertainties and fear, there are speculations about why the magnetic field cracked open. People began to speculate that Cern was opening a door through which something from another world could pass. Aliens, maybe? After the release of the news, which was accompanied by other strange news, experts said there is no cause for concern despite that there was a hole in the magnetic field. The experts agree that while the hole was open, it allowed strong solar winds to pass through the Earth's magnetic field. Although it is rarely talked about, it is very important to every living organism. It also keeps the ozone layer from being destroyed. Concerning the solar wind, NASA scientists say that more study needs to be done to study the total extent of their effect. The crack has only shown there is a problem with the strength of our magnetic field. If there is a problem there, that means we are not safe as nothing is protecting us from the sun. Or we could say that the sun, which we depend on for survival, can easily turn out to be our worst nightmare. There seems to be nothing that we can do from here, especially since scientists have told us to remain calm. But if there's anything that can be done, what do you think it would be? Run away to Mars, whose magnetic field has been ripped off, or find a way to strengthen our magnetic field? Let us know in the comments section. Thanks for watching. We'll see you in the next one.